And we are live. So I scheduled the stream on. Okay, yeah. So it's working. Okay. Cool. So we are live, and yeah, I hope the audio is clear enough. Cool. So okay, yeah. So it's good quality, and thing. Yeah. So we have solved all the six problems of Advent of Code, and we have solved both the parts. And yesterday I wasn't live. I was busy outside, so I couldn't come live yesterday. So today I will be solving both the problems, problem number 7 and 8, um, and I'll obviously solve them in Go, but then I'll also port the code to Rust and Zig. In the end, we'll try to understand the Rust code as well as the Zig code and how they work and what's the difference that we see as compared to Golang. So that would be a good learning experience. We have two problems to take care of, and both of them have two parts. I've already read the problems, and the first part for both of them doesn't seem to be that tough, but I don't know about the second part. So let's get started. Mm, Okay, so I hope everything is working fine. Mm, Okay, so I'll keep checking the chat for YouTube as well as Twitter. If there are any questions, I'll try to answer them. So this is the problem seventh. Mm, I'll just read this part to at least read the input because I'll have to write the repetitive code back again, which I don't want to do. This is day 7 and also day 8, but we'll solve day 7 for now. I'm initializing the package here, and this is our read input function. What I want from this function is only this part, which is okay. Read input, and I'll just skip this for now. Mm, okay, we'll call read input first. We'll also create input.txt file, which stores our input. Okay, now coming back to the problem. So what we have is actually a sort of a map, and we have the source, and then we have these emitters, or actually they are splitters. So a ray starts traveling from S downwards, and once it sees a splitter, the ray divides into two. So if there is a splitter at this position, then you can see that the ray goes to position, like in the same row, it goes to, like, it starts from j minus 1th column and j plus 1th column, and it starts going downwards. So it will keep going downwards in the same way, and all these dots are empty spaces. And once it again sees a splitter, it will split into two again. And this way it will just keep on traveling down until it reaches the end. So this problem is easy to understand. The problem here is that how many times will the ray be splitted? How many times it will be split? No, I don't know whether splitted is a word or not, but how many times this ray will be split? And clearly, if you just see this diagram, then the ray touches all the splitters except one. So if it touches like n number of splitters, the ray is split n times. And the number of splitters here are 22, I think. Mm, So actually, if you just count the number of splitters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. So there are actually total 22 splitters. But since this splitter is just below this one, the ray won't touch the splitter. And even if, like, let's say some splitter is far away, so let's say that we have a splitter here. This map is like let's just extend this map and we have a splitter here. Even that one won't be affected. So my initial thinking was, since this splitter lies below this one in the same line, we won't touch it. But that is not the complete picture. We have another splitter which is like far away from all of these. So the ray won't even reach there and it won't touch that one. So basically, out of all the splitters that we touch, that is the number of times we are being split, and that is the answer. So if there are n splitters and we are like getting split by x number of splitters, so the answer is x. In this case, we have like 22 of them, and we are being split 21 times. This one is not touched at all. Basically, we just need to traverse this matrix and maybe have a map and mark the splitters that are being touched here. And if it is not touched, then we can simply say that okay, we are not like touching them. So if the total number of splitters is n, if n is the total number of splitters and we are not touching x of them, so n minus x is the answer. Or we can simply say that if like we are touching x number of splitters, that is the answer. And how do we do that? We just traverse this matrix, execute this thing step by step, and the number of times we see a splitter, then that is the answer. So this is it. Basically, we need to return a grid. So this grid is actually uh, an array of strings, and each string is a row in this input. I'll just read this line and append it as part of the input and return this. And return grid. So this input is simple and we have this grid. Now, what we need to do is I can also have the number of rows and the number of columns. Rows, columns, n rows and n columns, which is equal to length of the grid. So we have like these many number of rows, which is length of the grid, and for each one of them we have the number of columns. And we know that our input is valid, so we don't have to worry about like error handling here, but obviously not in prod, never in prod. So we have like number of rows and number of columns, and we have this special character s, which is actually the source of the grid. And what we can do here is actually just mark all the positions where this ray appears, and also if um, so what we can do is, let's make an array. I'll call it as points. So these points are actually these singular points, like even the splitter, the source, wherever the ray travels, and this dot, like the empty space. So these are the points we have here on the grid, and we want to make an array of int, which is like number of rows, and for each of them is equal to make number of columns. So we have initialized our array here, which is like n cross m matrix. I'll just call it as n cross m because that is easier to think about and not too much of a tongue twister like n columns, n rows. Yeah, so we have like n cross m grid, which is the map that we have along with splitter, empty spaces, the source, and even the rays that we see at a later point of time. And now we have this matrix, which is called points. And let's have different kind of state. Type int state. Like even state is not the correct word here, but I think it's good enough for our purpose. Um, we have like const. We have the source. So source will be the state 0. It will be defined as the state 0. And then we have empty, which is the dot we have. Um, should I like call this as iota plus 1? I'm not sure. I'll just call it, like read it as 0, 1. And then we have splitter. And then we have array. So these are the states we have: source, empty, split, array. And so for each of the okay, so we'll just go through the matrix once and mark our initial states: I less than n, I plus plus, for j equals 0, j less than m, j plus plus, points I j equals something. So like switch grid ij. If it is source, then points ij is equal to source. If not, then if it is empty space, then we mark it as empty. I think it's better to make this a state only. Then case splitter. So we have all these states of the grid. Okay, I think this is a better way to write about it. So instead of like looping from 0 to n, we can have like range n, which is cool. Okay. So as of now, we have only this thing because we don't have any ray on the grid. Now, what are we going to do? Hmm. So there are few possible things that we should think about. We can have a function called traverse, which just traverses the points and just does an in memory thing, like not in memory but in place thing. So um, it starts with the row number 0, and also the number of rows we can have. So function traverse will take in the state. I think instead of points we can just call it as state. So it takes the state, and we can call this our world. So this is our planet, our world, whatever. Like um, we have this like compressed ecosystem that holds every possible state that we can think of, and we start with the first row and total rows. I think we can just call it as n comma m, where nm is the total number of rows and columns that we can have. Now, if I greater than equal to n, then simply return. Because then and I can what okay, cool. Cool. Okay, we have, so we can just think of two states like splitter is on and splitter is off. Because if we have seen a splitter, maybe we can also mark it as empty, but that's okay. For now, I'll just mark it as splitter off, and I think we can be sure that we have only one source which is in the middle. They have not told about it, but okay, they have not revealed the position of S, but if we just look at our puzzle input, it is somewhere in the middle. So I'm assuming it's in the middle, but but okay, wow, this is very large. Um, so initially we have splitter on, and once we have seen the splitter, we can just mark it as splitter off, so that we are sure that when we are counting the number of splitters which are off, that is the answer. So let's run this simulation. I'll, instead of calling it as traverse, I think a better way is to call it as run simulation. So if I is greater than equal to n, then we simply return, and for j equals 0, j less than m, j plus plus, or like as we learned today, it should be range m. So for all the j, like in this current row, for all the columns, we are just updating the state once we go over it. So what are we going to do here? It would be, again, we can have a switch case here, and I is the current row. So if state ij, if it is source, um, if it is source, if it is splitter on, if it is a ray, these are the things that we are concerned about. If it is a source, then we can just have, we can just update the state downwards. So for example, if this is our source and the lower, like just below the source, now we will have a ray. So initially it was empty, but now we have a ray because the source has started emitting this beam. uh, I can just say state I plus 1. State uh, okay, it is actually n minus 1, because if we are at the very bottom, then then there is nothing that we can do. uh, okay, and just to confirm that in the input, are we going to have anything in the bottom? Okay, so the bottom row, as you can see, is completely empty, so we don't need to worry about it, but even like this algorithm should even take care of that. So if we are at the last row, we do nothing, we just return. uh, Stop the simulation. Since we are at the last row, we will just stop the simulation and state I plus 1 j equals ray. So now we have this ray that is produced just below this. Now if our state has splitter on, like this is our state and our splitter is currently on, and if it sees that just above it we have a ray which touches it, then this splitter would be turned off, else we would do nothing. So if state um, I plus I minus 1 j, if there is a ray just above it, then uh, then we can modify the state. So state I j would be splitter off, and state I j minus 1 would be uh, now we have a ray here, and similarly j plus 1 has a ray. So if you just look at the splitter, now we have a ray above it. If there is no ray above the splitter, then we don't have to worry about it. If there is a ray above the splitter, only in that case the splitter we are turning it off, and then we are initiating like two rays just on the sides of this. So that is okay, and we just have to add some checks here. If I is greater than 0, and so this won't matter because we know that we don't have any splitter on the first row, but I'll just add this check just in case. So if I is greater than 0 and this condition holds, then state ij is splitter off, because currently that is splitter. So it was splitter on initially and we are just turning it off, and then I j minus 1 is a ray, and we'll just add another condition here, like if j is greater than 0, then do this. If j is less than m minus 1, like we are not in the last column, then do this. So we can only initiate a ray if it is like within the valid bound. So this is another thing. And now if we have a ray, so what can be the different states that we have? So if we see a ray here, then we don't have any other option but to mark the one below as a ray only. Like there are many cases that we are missing because we know like those cases won't occur here in this problem. So if we have a source which is only at the top, then we are marking the below one as ray. If the splitter is on and we see a ray, then we turn it off and have initiate two rays just on the sides of that, if like it fits, if the positions fit within the valid bounded range that we have, like n cross m. And if we have a ray currently, then, and if the below one is empty, we mark it as ray. If the position just below the ray is a splitter, we leave it as it is because that is handled in this case. So that is splitter on case. And we won't have a splitter off case because mm, can we have a thing where we have already seen the splitter from some other array, but no, since we are processing it row by row, I don't think that will also happen. So if I less than n minus 1 and state I plus 1 j is equal to ray, sorry, so it is empty, only in that case we will mark that as array. So this is what we do, and we continue. This is the simulation that we run for this row and for all the columns, and then we continue running the simulation with our modified state array, and I will be incremented to 1 and n and m information is preserved as it is. So after doing this, we'll just count that for, so for this thing, if state I j is equal to splitter of, then count plus plus. So this is our answer, fmt.println count, and let's try to run this. I'll take this input. So the answer is 22, which is incorrect. So the answer is incorrect because for some reason we are switching off the splitter. So this splitter was above that, and hmm, I'll also print this state array, state j, sorry, state I. Okay, so this is it. What's happening here? I mean, is this even correct? I think this one is empty. So I'll reverse this. Oh, because we have marked the state as same, and this is why we had this silly mistake. And the state is marked as a same integer, which is 2 in both the cases. I mark them as 2 and 3 now. And let's see. Now we get 0 for some reason. Mm, I don't think we are anywhere using any sort of number. So I'm not sure why we have like everything as 0. And first of all, why do we have like such a large array? What is n comma? N is the number of rows. rows, columns. So we have like 16 rows and 15 columns. Um, okay, like seems about right. I won't count it. Mm, but it surely doesn't seem like. Okay, this is what. This is why we were printing everything, which seemed kind of wrong. Mm, okay, so somewhere I know that we had a source here somewhere, but two, we are only seeing two, which is splitter on. For some reason, this simulation did not work. Mm, is this thing? I thought that maybe like in place modification or something did not work, but mm, so we can only see like two numbers here, 0 and 2. 0 is the empty state and 2 is splitter on. So we haven't even marked source here, which is pretty weird because it is j comma I, which should be actually this. So now since we did not, like, this is so funny, so since we did not even had a source marked here, we did not even start this ray traversal thing because it did not find any source, and for some reason now it for some reason now it has marked it as 4 3. mm, I'll also translate this to something ij. So this is correct, ij, like we have not reversed the index anywhere, so we have not done that mistake again. Hmm. So we have this state to grid function which takes in the state array, and it also prints state to grid. Okay, so this assignment doesn't work because we'll have to do this bytes of grid. I Why do I make things complicated all the time? This is empty. We could have done everything on this same thing here, but mm, okay. Uh, okay, cool. So this is the problem. For some reason, it's not taking the ray above us. I think I know what the issue is. Um, so if it is a ray and I minus 1, okay. Hmm. So I know what the issue is. The issue was that since I marked this as ray in this first iteration, now this ray, like the ray below it, the space below it should also be marked as a ray. But that is an empty thing. So an empty space would only be modified if there is one ray above it. So we also need to account for that case. If I greater than 0 and state I minus 1, this was interesting. If it is a ray, then state ij is equal to a ray. So if I have a ray above me, I will mark the below state as ray only. And I think then this can be skipped. So we don't have to, if it is a ray, we do nothing. So if it is a ray, we do nothing. If this is an empty space and we have a ray above us, then we mark ourselves as a ray. And if we are a splitter, then we just construct the rays on both the sides, given that they are within the valid bound, and we turn the splitter as off because we will be using it for our calculation. So to run this now, we are getting the output as 21. I'll quickly just paste this input here and also run this. Now we have 1,555 as our answer. So 1,555. Quickly also check if okay. Okay, we don't have any chat here, so okay. Yeah. So we can continue to part 2. So we were able to solve part 1 by actually running the simulation, and this was pretty cool. We did run everything here, and so we just like did a recursion to run the simulation. And the very basic thing that I can say is that in case of recursion, you should handle the states very well. We were not handling the state very well here, and that's why we were seeing a wrong answer. Mm, So this is done, and now we come to the part 2. Mm, In one timeline, the particle went left, and in the other timeline, it went on this path on right. So basically, we need to have all the possibilities here. Like if the ray goes on the extreme left or on the extreme right or somewhere like through a path in the middle. So we just need to account for all the possibilities here. How many different timelines would a single tachyon particle end up on? Okay. Uh, okay, so we need to find the number of different timelines. So basically, this comes out to be a path, like that problem where we count the total, I think path counting or something, where we count the total number of paths we can have. So basically, this is it. We just have to count the number of paths and nothing else. And since we are already storing the state, I think once we run the simulation, we have all the states visible to us. And in a way, we are just doing this dynamic programming thing where a state is actually the combinations of all the state below. Hmm. Like, obviously, the state, like when we hit a splitter, only in that case, like we have two different states, two possible states, and they might end up into like two more different states. So we like for this splitter combination, we have four different states. The one with rays traveling to the extreme left, then to the extreme right, and uh, so one, I'll just make a diagram here. So this is our first state. I'm just like talking about this combination. This is the second state, then this is the third state, and this is the fourth state. So dpij, like for this splitter, we have all the states that is possible down below. So like for this splitter, we have like these four. If we just consider till this point, we have like four different states here, and then we have like four different states here. So we have like eight different states for this splitter. Okay, it's a mouthful, like states, splitter. Okay. So how do we go about this? I think we can do the same thing. What we can do is we can so let's say that we only have this splitter, and the ray falls on this and goes like this, and this is the end. So if we have like these two rays, then we can just mark it as 1 and 1, and this is the position. I'll just change the color here. Okay, we have a splitter and we have two rays, and this was the ray that came from the source, and Now this is 1, this is 1. Now when we come to this point, like when we are iterating bottom up, we are iterating over this row first. We have like 1 and 1 stored here. Then we are going up, and this thing would be marked as just 1 only. So like, so we saw ray at the bottommost row, then we saw the ray again just above it. And so when we encounter a ray like on any other row, we will just copy dpi plus 1 to that. So this is dpi plus 1 comma j. This is also dpi plus 1 j. And when we see a splitter here, that is actually the combination of this and this, because now our paths, so our path is the number of paths we see from the right side, from the left side, as well as from the right side. So if it is a splitter, and the splitter should be in off position, so the splitter should be in off position, because that's the splitter that was active before. The one that is already on have has nothing, so that is also cool. Mm, okay. Then similarly for this ray, we have the number of times. Um, so there are a few cases. If it is a ray, that is simply dpi plus 1 comma j, the number of paths. Uh, okay, so this is part 1. Now let's make a dp array. Finally, we have a dp problem here. I think maybe we can also solve it in some other way, but dp is pretty cool. We have n rows. Mm. We have m columns. Mm. So we start from the end now. So we iterate over all the rows and we start from the end and switch state. Actually, we start from the second last position, because we know that for the last position we have like, if state I j I is actually n minus 1, since we are at the last row, if it is array, then dpi like dp n minus 1 j equals 1, since that is part of the path. Now for all the rows, um, for all the rows here, and we also do this thing where we have like answer which is equal to max of answer comma dpij. If it is case, if it is array, if it is array, then dp ij is simply dpi plus 1j. If it is splitter off, then, and obviously if I greater than 0, sorry, if j greater than 0, and if j less than m minus 1, then dpij, since now we are just summing, since we know that the splitter is in the off position, we are summing the left and right side because both of them were rays. Since both of them were rays, I'm actually thinking of the case for this one. Like if we have like two splitters side by side, then if then the path in the middle, will it be counted twice or only one time? So that is something I'm thinking about. I think it will be counted twice because because first of all, if like there are two cases. Actually, there is only one case. So since this is a common ray, we know that it is common because a ray must have seen the splitters on both sides of this one. So we know that this is one unique path, and the second path is actually a unique path. So for the sake of this path, we must count it once, and for the sake of this path, we must count it once again. Therefore, we will count it two times. So dpij equals dpij plus 1. Mm, and this won't work because now we are doing the same thing again. Actually, actually we must handle this ray case separately and the splitter off case separately, because then we will run into the same problem where we are modifying this, but since this hasn't been modified yet, we are not counting it as part of the splitter. I think, yeah, that would be better, but I'll just write it for now. I j minus 1. Mhm. Yeah, so this is one and this is the other. uh, and answer is equal to max of answer comma dpij. We'll just calculate the answer at this point only. I think this should be okay. So we can have only 2 to 3 cases. If we have a splitter off, we don't consider, if a splitter is still on, we don't consider it. If it is a ray, then we just do this thing where we assign the dp state that was just below. um, oh, actually this will be completely separate. Paths is 0, which is again wrong. Oh, so this, like, nothing changed here. Oh, is it because of this thing? Because we did not modify the state where the last row is array. So we can just go ahead and do that just here. Uh, where is that? So when we are running the simulation, we will also run the simulation on the very last row. I was not running it because I wanted to avoid one of the cases here, which is this case. So I'll just handle it if I less than n minus 1, then this. If we just go to the last row, then, like, if we go out of bound, we return. Earlier I wasn't doing it because I did not write this condition, just to, like, prevent that bound access or handling. So paths is now 40. Now we have like 40 different paths, which is cool. I'll copy the input. These are the number of paths, and you can see that if we had went through the path of recursion, traversing all these paths would have, like, taken infinite time. So we would need a quantum computer to solve that efficiently. uh, but now, since with the help of DP, we were able to solve this pretty quickly. So this is correct, and we were able to get one nice gold star. And this problem was fun because, first of all, it was one of the standard problems, and secondly, we also printed all the state and everything. So we know what is going on here. It's not that we are just using DP and everything. And we were also able to solve this in a very elegant way, where we did proper state handling, and that is a lot. So just to summarize the problem, we had different states. We modified the states by running a simulation. So that gave us the very first answer, where we had the number of splitters that were being used. And after that, we also printed the state very beautifully. That was pretty cool. Then we used DP, dynamic programming, to find the number of paths. And again, that logic was very simple. If you look at the dynamic programming logic, this is it. This is the logic, which is pretty cool. And DP, state, and M. So we have DP, we have state, we have N and M. Okay, it returns int, which is the answer. So this function is number of paths using dynamic programming. Cool. So this was day number 7. I'll share the solution on Twitter after some time. I'll also have a look at the chat. So, Who is this guy? I Okay, someone who is obviously not real, because I thought for a moment that it's the original guy, but he's not. So yeah, doesn't matter. Obviously, we don't have any views here, but cool. I think maybe someday. Now, coming to problem number 8. The elves are trying to figure out which junction boxes to connect so that electricity can reach every junction box. They even have a list of all the junction boxes, positions in 3D space. For example, this describes the position of 20 boxes, one per line. Each position is a given XYZ coordinate. So the first junction is at this. To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are as close together as possible. According to straight line distance in this example, the two junction boxes which are closest are these two. By connecting these two, because electricity can flow between them, they flow blah 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 circuit. There is a single circuit and the remaining 18 own individual circuits. Now the two junction boxes which are closest together but aren't already directly connected are these two. After connecting, we have now like three junction boxes and 17 are left alone, like they are single. The next two junction boxes to connect are this and this. After connecting them, there is a circuit containing three junction boxes, a circuit containing two boxes, and 15 circuits which contain one box each. The next two boxes are these two, because these two are already in the same circuit. Are they? Okay, 425, this was connected initially, and 431 was connected later. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They would like to know how big the circuit will be. After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 boxes, one which contains 4 boxes, two circuits containing 2 boxes each, and 7 which each contain a single box. Multiplying together the sizes produces 40. After making the 10 shortest connections, since they're okay, so like we have these boxes, and these are in 3D space, not in 2D space. So, but the way the distance is calculated is almost similar. Now, in the first iteration, we connect the ones which have like shortest distance between them. In the second iteration, we again connect something which has like shortest distance. Then in the third one, like these two already have a shortest distance and they are part of the circuit. So it is still one single big circuit. Similarly, in one of the iterations, we connect this and maybe this, like these are the shortest distances. And we have like three circuits here, which are like set of boxes that are connected together. And the distance and the way we connected them is that they had the shortest distances. So we are just iterating over the shortest possible distances and then connecting the boxes. If they are part of the same circuit, like these two were, we are doing nothing. If they weren't, we are connecting them, like we are making them part of this bigger, like the existing circuit. So I think like there is this set of problems called union set or something, where we make a parent set, and yeah, So we can just do this union find. That's an algorithm where we just make everything part of one set. Like we can do this in brute force ways also, but I think making proper structs would be a better idea. Your list contains many junction boxes, so I don't know how many of them are there. And connect together the 1000 pairs which are closest together. So we need to repeat this thing 1000 times. After, what do you get if you multiply together the sizes of the three largest circuits? Then we need to take the three largest circuits. Maybe we can have a heap of size 3 and then just keep like pushing the maximum 3 elements then, or we can simply like sort them all and take the top 3. So I think that would be even easier. So first of all, I need to understand how many inputs are there. Okay, it's a large list. Something, maybe something that can be solved in n square thing, because I need to find the distances between the two boxes. This is day 7, which is okay. CD day 8. Mm, I just copied this to read the input so I don't have to repeat myself again. So I'll just remove everything and I'll have this function called read input. And obviously now we have like these numbers, so we need to do the number parsing again. For now, I'll just copy this input. I'll call it as input test, and then input dot large dot text, and this is input dot small dot text. Cool. So I'll call this as a box. Okay, first of all, these are comma separated values which are numbers, and we have a function parse which does the parsing from line to a box. And what is this box exactly? It's a struct which has like 3 coordinates x, y, z. I don't know if these numbers are positive, but like they can be negative also. It shouldn't matter to our algorithm. And this will give us s base int bit size 0. Or I'll so we need base 10 and bit size is 64. Okay, so this is it. And now I need to have sorting here defined. So I'll just have like a sort function because I'll be sorting these boxes. Okay, I don't think I'll sort these boxes. So we also have a circuit, which is like a combination of boxes. We have a circuit which has like a set of boxes, and we can also store the indexes because I think we might need them. Hmm. And the thing is that we want to make a box a part of the circuit, and basically joining we are joining like two circuits together. Hmm. We are joining like two circuits together. Hmm. Okay, so each box is defined as a circuit itself, and when we are combining two boxes, basically we are combining two different circuits. Let's say that this was the shortest distance, then we have this distance, which is like a circuit is created again, and then we have this third distance. So now these four boxes will become part of the same circuit because this was the third shortest distance, this was second, and this was first. So now we have one large circuit with all the three boxes. If two boxes are already part of the circuit, we don't do anything because they are already part of the circuit. In the end, we have to just see that what are the sizes of all the circuits, which is easy to get, because it's the length of the boxes we have. And the way you do this union find is that you also need to have a parent, like the leader of that circuit, or for a set, like you need to have a parent set. And for okay, first of all, I'll what I'll do is I'll just parse this to a box. Now we have like boxes. Make box comma 0. Now we have boxes, which is an array of box, and for each line uh, then for each line in the grid, or I'll just call this as input. So for each line in the input, I'll convert that to box and add it to our boxes array. Parse line. In fact, what we can do here is for Index comma box in range boxes. Now we have another array which is like an array of circuits. We have like circuits. So for each box, we'll convert it to a circuit. Uh, so parent is actually the index. Or I can I don't think this is the best way to do union find here. So I had this, like I did this algorithm a long back, but what we need to do is like, let's say that this is a set. This set has like three elements to it, which are like all connected to each other. And the next shortest distance is the distance of this element, which is outside the set, to one of the elements here. And let's say that let's say that this is the parent, like this is the leader of the set or the parent of the set. So the parent of this can be the second element, and the parent of this would be the first element. So what we will do is we will recursively traverse to the parent, and then we will increase the size of the parent itself. And this is like adding one element to the set. But we might as well have another set that needs to be added here. So now we have like two parents. So the size of this set would be the size of this set plus size of the parent of the other set that we are combining it with. Because it might be the case that we have this other element which is like closest to the second element. Then we find the parents for both of them. We find the parents for both of them, and then we merge the set by assigning the parent of this set to the parent of the second set, which is a very beautiful way to like combine two different sets. So this is the union find algorithm. Interesting. So now we have the boxes and we have the indexes, and circuit is actually just a circuit will only contain two things, which is the parent and the size. The parent and the size. Cool. So initially the parent is itself, and the size is 1, because we have like one element in the sets, in this set. uh, and then we have like, we need to find distances between two different elements. We need to find distances. So actually, um, we have this thing called distance, for which we will actually implement the sorting part. Which is nothing but like modulo of x1 minus, uh, let's say that we have the elements, like we have the coordinates as x1 x2 x1 y1 z1 x2 y2 z2. So this is nothing but x1 minus x2 plus y1 minus y2. We can also have square of this function, but this, like for our intent and purposes, this is also fine. 1 minus z2. This is what we want. And also the indexes, where we can have like an array of index, but I'll just call it as index 1 and index 2. So these are actually the index of box 2 and index of box 1. So we have the boxes, like initiate the sets, initiate, oh my god, initiate, okay, initiate the sets or the circuits, and then like find the distances between the boxes for I equals range n, where n is actually the total number of boxes that we have. For j in range n, actually it is for j equals I plus 1, j less than n, j plus plus. So we have this distance array. We have this distances array, which is the distance between the two boxes. So what if the distances between the two boxes is same? Hmm. Oh, actually we will have to first of all do the square here. Actually this will be power 2. I'll explain why this can be a bug. For example, if there are three elements, 1, 2 and 3. Let's say the distance between these two is 5, and similarly the distance between these two is 5. Then which one are we going to choose? Here the 5 is actually 1, 2, 2, and here the 5 is actually 1, 1, 3. But this is not the correct distance. Both of them sum up to 5, but the squares sum up to 4, 2 to 4, like 4 plus 1, 9. And here the actual distance is 11. So we will have to choose this pair first. Therefore, it's not that we can just take the modulo thing here, but we need to square the distance. That is the right way to do it. And let's say that if two boxes have same distance, then what? After making 10 shortest connections, there are 11 circuits. Can we have like different, can we have like same distances? If we have the, I don't know what, like how is it being handled, but let's assume that the same distance thing is handled by the problem statement itself. Like the input is such that it handles the same distances formula, because they haven't mentioned anything about the distances being same. Okay, so we'll just do what the problem statement is telling us to do. uh, yes, so we have like, what is the distance here? It's actually d, and d is actually boxes I and boxes j. Each box has x, y, and z. So it's x2, y2, z2. This is I. This is 1, 1, and 1. x1 minus x2, y1 minus y2, and z1 minus z2. So this is the distance, and index 1 is I and index 2 is j. So now we have the distances array, and this is again wrong. This is box I, j, x2, y2, y1, y2. Okay, so this is correct. Now what are we going to do here? We will just sort this. So we are sorting it on strict less than and not less than equal to, because we don't, obviously this won't affect anything, because because we are already changing the values here. So we are already calculating the distances. After we have calculated the distances, we are now sorting it. So now let's sort it. Sort dot. Now we are sorting this distance array. Now once it is done, what are we going to do here? Okay, for each distance, if it is shortest, we merge it to the set. And we do it like 10 number of times. How many times are they doing this? After 10 shortest connections. So we can just take this as 10. I think that is also okay. If so how do we merge the circuit? I think there is a function called find. We must find the parent of circuit 1. We find the parent of circuit 2, and just going to this find function. Actually, just let's just take a circuit, not a pointer. And also the index where we are at. So if index is equal to c dot parent, if we are at the same circuit, then we return index or parent. I think it's better to, like, for readability purpose, we return the parent. Finds parent of a union find set. And similarly, if not, then we go to um, so we take in the circuit array, that is, we take in all the sets as well as the index for which we need to find the parent. So if the index is equal to the parent itself, we return it. If not, then we just move to the parent of this circuit. So, like, parent of that index. So let's say that these three are the ones that are connected. If the index of this thing is equal to the parent of this thing, which is not, so the parent of this box is the one that is above it. So this is the parent of this child box, therefore it doesn't match. We go to the parent of this box. Now we repeat the same thing again. It's not equal, we go to its parent. Now the index of this is equal to the parent of this, which is the box itself, so this is the one that we are looking for. And how do we merge two circuits? uh, so it is find c1 comma c2. uh, how do we merge? Actually, it will be two index. How do we merge two indexes? And we also take our circuit array. uh, so it will be our circuit array and I1 and circuit array I2, that is the parent 1 and parent 2. If parent 1 equals parent 2, then clearly they're part of the same circuit. They're part of the same circuit, so we just return. If not, then so the second circuit becomes part of the first circuit. Basically, if we have like two different circuits and our parent is here at the top, then the parent of this circuit becomes the one here, and the size become, like, we add the size of the second one here. So c of parent 1 plus equal to c of parent 2 dot size, and here it will be dot parent dot parent. So we are modifying the array also, which is cool. So the parent of 2 is actually the parent of 1. Okay, and the parent of 1, like the size of the first circuit increases. So this is the union find algorithm where we have this find function and merge function. Merge two union find sets. I don't know whether we called it as union find sets, but uh, or we can also call it as union. Actually, find and union, or find or merge. We can have like any name that we want. Okay, so let's see that for this 10 thing, we are simply merging. Mm, we are merging. We have the circuits and distance 1 dot index 1 distance dot index 2, or so we are calling it as union. So now we have each of them merged. Okay, and what are the sizes that we have? And also we need to store the circuits, the parents that we have already seen. So it will be make map. So we need to store the parents that we have already seen. Range circuits. I'll call it as C. So if not seen, C dot parent. Okay, and it's not, it is actually circuits then. C dot. I don't know why it's not working, because circuits is actually an array of circuit. And I'll call this as set only. So this is a union find set. I think there is some other issue. Okay, and union set. We have like, we have these sets. Okay. If we have not seen the parent, then seen c dot parent equals true, and other than that uh, we just store c dot size. So I'll just print, I'll finally print the size array. And I'll also see that we have the proper inputs, and it is actually input dot small dot text. So we have 3 1 5 2 2 whatever, and 5 which contains 4 junction boxes, 2 circuits which contain 2 boxes each. So it should be 5, 4, 2 and 2. 5, 4, 2 and 2. So for some reason it is 3. Uh, okay. Are we doing size as 1 when we are initiating the circuit? Okay, size is already 1 when we are initializing our circuits or our sets. Three largest circuits, 5, 4, 2. So the three largest circuits are 5, 4 and 2. Where is it? And actually it is so again slices dot reverse slices dot sort. Okay, it's actually ends slices dot sort ends and it will be size, and then we just need to reverse it. Okay, it does in place reversion and in place sorting, so we just need to print size, which is incorrect here. So it should be 5, 4, 2 and 2, but for some reason it's only 3. I'll just print the distances, like the top 10 distances. So the first one that it's talking about is 0 and 19. 0 and 19, 984 and 162. Which is wrong. The two which are closest together are 162 and 425. 162 and 425. Okay, which is correct? 0 and 19. 0 and 19 and now the two junction which are closest together are 162 and 431. So is it 0 and 7? 162, 0, 1, 2, 3, 4, 5, 6, 7 and 431, which is again correct. Nine zero six and 805. The next two junction boxes are 906 and 805. There is a circuit connecting three junction boxes, a circuit, two junction boxes. So 906 and 805. So 2 and 13, 9, 906, 2. This is 19, 18, 17, 16, 14, 13, 346. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's telling me that it's 2 and 13, but that is not the case. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, it's saying it should be 431. Okay, the closest together are 162, 425, 162 and 425, which is correct, 0, 19. The second one should be 0, 7. But aren't already directly connected. Are 162 and 431. 160, 0 and 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay, and we are connecting them. After connecting them, since this is already connected to another junction box, there is now a single circuit which contains 3 boxes and an additional 17 circuits. The next two junction boxes to connect are 906 and 805. and 805. 906 and 805. This one. 906 and 805. Is it 2 and 13? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, which was correct. I don't know why I was confused. After connecting them, there is a circuit ending 3, a 2, 15. The next two boxes are 431 and 425. Let's see. Is it 7 and 19? Mm. So 1, 0, 1, 2, 3, 4, 5, 6, 7, 7, and 19. 431 and 425. Hmm. Why aren't we getting this thing as 4 here? There are 11 circuits. One circuit contains 5, 4, 2 each, and 7 circuits which contain a single junction box. 4, 5, 6, 7, 8. What is the size? So the length is 13, which is wrong. After making the 10 shortest connections, there are 11 circuits. Why do we have this as something which is greater than this, which is correct? Okay, yeah, it is sorted from low to high. So that is fine. And we don't have anything that is same in length, and all of them are unique lengthwise. Hmm. All of them are unique. Then what's the issue? After making the 10 shortest connections, now we have these sets and we have these indexes. Mhm. Why is this not working? Okay. Mhm. Yeah, this is. I have no idea why this is not working at all. After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 boxes, one contains 4, two circuits which contain 2 junction boxes. Mm, and if we have seen the parent, so I think this is correct. If we have not seen the parent, then oh, because yeah. So the issue here was that uh, let's say we have like these three circuits, then I need to find the parent of each of them. But I was just thinking about the immediate parent, but that might not be the case. I want to take the the main parent, the one that is like representative of this whole set. Yeah, and this was the issue. So because of this line, I had all the wrong answers. Now it will be 11, and we have like again it is 5322, which is wrong. Hmm. Is it because of this? Because I messed up the ordering, although this shouldn't affect anything. Hmm. Is it some one-off error? Now I'm just like doing silly things. This is not a one-off error. Uh, am I doing it for all the boxes? So I know that I'm finding the distance for all the boxes. N is the length of boxes, which is okay. And for all the boxes, I'm taking like I'm iterating over all the indexes. So x1, y1, z1, x2, y2, z2, x1, y1, z1, and then boxes I and boxes j, xyz, distances, um, distances is actually distances comma distance, which is ij, which is fine. So I'm taking both the indexes. Am I missing something here? Like, am I missing a pair? Okay, this also did not fix it. Mm, let's do it 11 number of times. Which did not change anything. What if we do it all the way? Okay, if we keep doing it, then we have only this thing. Okay, okay, I know the issue. So everything is correct. We should do it 10 number of times. We have to do it like 10 times. But the problem is that once we have found the parent, then it should be sets parent dot size and not this one, because this is the current set and we want to find the parent first, and so whatever we have to do, we have to do with the parent. So always find the parent. That's how union find works. Now it is 542, which is correct. 5420, 2240, which is okay. Now I will have this large input, and the number of times we have to do it like 1000 times. It will be file path and the number of times we have to do this. So initially the file path is input.small.txt and times is 10, but now we have to do this 1000 times, and the file is input.large.txt. And uh, size 0, size 1, size 2. I can also comment this out. So it is 123930. And this is the correct answer. So going to part 2, the else were right, they definitely don't have enough extension cable. You'll need to keep connecting junction boxes together until they are all in one large circuit. Continuing the above example, the first connection which causes all of the boxes to form a single circuit, the else need to know how far those junction boxes are from the wall so they can pick the right extension. Multiplying the x coordinates produces this. Continue connecting the closest unconnected pairs of junction boxes until they're all in the same circuit. What do you get if you multiply together the x coordinates of the last two junction boxes you need to connect? So now we have all these circuits that are there. Let's say that we have like in the end we have like these two sets with us, and obviously like there is one set here and the other set here. The parent of these sets can obviously be different. uh, the parent of these sets are here, and we are connecting these two sets actually. So we are connecting these two sets, and we must do it until the size of this whole thing is 1, which will eventually happen. So we have like all these distances array, and we need to keep doing this until we have like one big set. And the first time that happens, so the distance array that we have, we need to multiply the x coordinates of those distances. So basically, how do we make sure that we have like a single parent available? So we need to count the number of distinct parent in each run. Okay. So this thing is okay. This is the answer for part 1. Assuming that these many number of runs don't do anything, because obviously we had like one large list even after this, so it means that the circuits are still not connected in one large entity. So we know we can continue doing this from for I equal times I, there's no condition. So let's keep doing this. Let's keep merging the stuff. So now we are continuing with the formula, like with the algorithm here. We are just taking the next smallest distance and then merging those sets, like union, find, merge. And then we have to, if total parents, if total parents of this sets is equal to 1, only in that case we break. And we also have this x1 and x2 set, which is the x coordinate of this index and the other index. So basically it is boxes. So this is the index and x coordinate of this one, as well as x coordinate of the second one, x1 x2 -1 -1, x1 into x2. Okay, now we have to implement this total parent function. For so we need to find the parent of this, and we also need to have a map, uh, again the same map we can have, which is a map actually. So if so scene parent is equal to true, and then we have to return length of scene, which is the length of the map, the number of keys we have in the map. Yeah, I think this should be fine, but I don't know what will be the complexity of this algorithm. So it is 10 and it is small. So answer is 25272, which is correct. So this should also work for our case. Now we have 1000 and it is input dot large dot text. Okay, the answer is 273 and 38688. Uh, and yeah, so this is the correct answer. So we are on day 8 of Advent of Code, and we have been able to solve both the parts for all 8 days. And this was a pretty interesting problem. And obviously, if you observe here, this took a bit of time to solve. What we can do here is uh, we can do pruning. So, like, I don't know whether pruning is the right term. So let's say that we have three elements here. The parent of this is the second element, and the parent of second element is the first element. Then while iterating, we can also have this backtracking thing maybe, where we assign the parent to this one directly. So instead of like when we are calling this function again, like instead of going through all this long length, we are just doing this only one single hop, which will be faster. So this is kind of a great update that brings the complexity down to like very low. So it is almost like constant time complexity if it is being used again and again. So let's do that. Mm, and what we can do is see of, so currently we are at index. Parent can be set as the parent that we found. So this brings the complexity to very low, and the answer should be instant as compared to before. So this is one small optimization that helps us make this solution faster. So yeah, this is it guys. We were able to solve all 8 days of Advent of Code, and we were able to do both the parts. Obviously, we can convert this to Zig or Rust, but okay, let's just convert this to Zig and see what we get here. Convert this union find piece of code into Zig with proper comments and allocators assigned. So we are converting this to Zig, and let's see what solution it brings up. Obviously, we can try to understand that solution, and I have Zig already installed. Uh, okay, that is not the correct command. Is it Zig build? Is it Zig init? Zig init AOC 2025 day 8. Okay, I don't know how do I init this thing. Yeah. I'll also write a command to know how do I run this function. So you can see that how it's using allocator to dynamically allocate the memory and then it frees the memory once this function is over. And also, like, I don't know what is at the rate. I'll ask ChatGPT here. So what is at the rate functions and how do I init and run this program? Just copy this code here. So at the rate import standard library, we are importing the standard library, and then we are using these at the rate functions and mem copy and everything, which is like dynamically memory allocation, etc. So there is one error here, which is, I don't know why. I think union is a reserved keyword, so we can't just keep on using it. Okay, there are many issues here, but what I wanted to show is something else. Okay, it is trying to explain anything that looks like at the rate something is a built-in function. Okay, it's a built-in function provided directly by the language, not by library. So it's kind of a standard library. Obviously, we are importing at the rate standard, so it is a standard thing here. Minimum of two numbers, and then memset fills an array with a value. They start with at the rate. You don't need to import anything to use them. No standard dot prefix. Okay. How do I init and run this zig program? You have copied the zig code into main.zig. You have this zig version .zig. Okay, zig run main.zig is the command. And there are errors here. So I'll copy this at the same time, modify it to this, and this is the error. So there are some issues here and we'll try to fix it. While that is being done, I'll also look at the code here. So we have this GPA, which is generic program allocator or something. I don't know the full form, but it allocates the memory on, okay, it's general purpose allocator. So it allocates the memory on heap. And what is dot leak? I don't have any idea about this. Try returns an error. Here in this case, we have this read input function, which takes in the allocator and returns an array of array list. And this operator, like this exclamation mark, tells us that it can fail. So it can return null maybe, or an error, because try returns an error. So it can either be an error or it can be the array list of type U8. Okay, it's not that very easy to understand, but I'll let it be for now. But yeah, this is something that maybe I'll make a video on this next. By next, I mean at a later point of time, once I'm done with this advent of code problems. But let's see if we can fix this now. So it's trying to understand and update all the, like it's trying to understand the documentation and update our code to fix those errors. So I'll just paste this code on my Twitter feed, like via my Twitter account, and I guess I'll see you guys in the next one. We couldn't do Rust, but obviously Rust is like easier, but not that easy. We still need to get better at it. But obviously, like porting this code to Rust is a very straightforward thing to do. like especially to idiomatic Rust, because we are using all this sorting and everything. So yeah, I'll maybe we can do it next time, but for now I'll just copy this code and see if that works or not. And yeah, so the all of the issues are solved now. Maybe I'll try to explain this code uh, in the next video. Oh, is this like defining t at compile time or something? Com time t. Yeah, it's like very optimized in some ways. So we so I know for a fact that we have control of this dynamic allocator, which we can use to like create arrays and everything. So total parents does that. It like allocates. So so even in Golang we are doing the same thing, but in case of Golang, the garbage collector handles this behind the scenes. But here we are like doing it by ourselves. We are allocating the a Boolean variable. Okay. Okay, so the scene is actually a Boolean variable which is of sets.length and catch unreachable. So we are assuming that there won't be any error while allocating it, while allocating this Boolean array of length sets.length, and then we are freeing this thing, and at the same time we are setting the values to false. Because like this is a good practice that even in case of C we do this, like we do after malloc we do free and then we set it to null pointer, so that uh, it is first of all like it is phantom or false data or something and collected by the system or the garbage collector. But I don't think we have a garbage collector here, so yeah, I'll still need to understand how this works behind the scene. But yeah, so for sets, so for this array and starting from index 0, we have this thing, the parent and the index. Okay, okay, the value and the index. We don't care about the value, but we care about the index. Then we have this find function. I'll just run this if this works or not. Okay, there are other issues. So clearly this is not the correct code. This is still not the correct code, but cool. We'll do this in the next video. For now, it's getting late. So yeah, I guess I'll see you guys in the next one.